Today we want to calculate the resistance of a copper bus bar using the electric current module in COMSOL Multiphysics. Till now we have only considered the electric permittivity of a material. Now we want also consider the conductivity of that material to calculate the resistance. Moreover, I want to perform the simulation in the 3D domain because we haven't explored the 3D features of the software yet. Okay, I have opened the COMSOL Multiphysics. I go through the model wizard. As I told you, I select 3D, and here under the AC/DC and here electric fields and currents, you can find a module which is called electric currents EC. If you read the description here, you can understand that this module calculates the electric field, current and potential distribution in conducting materials. Therefore, it considers the conductivity. However, it only fits where the inductive effects are negligible, where we don't want to consider the skin effect or proximity effect, which I cover in another video. Okay, I click on Add and go to the study, and for now I only want to perform the stationary study. I click on Done and we go to the software. I close the Add Physics window. First of all, I go to the geometry. Here I set the unit to centimeter. And now I want to generate two bus bars, one of them in the shape of L and the other one in the shape of I, and they have a electrical contact to each other. Okay, you can go to the geometry tab and here you can find the block. I click on block. Here you can set the base coordinates of this block, and here are the dimensions of the block. I set the width, for example, to be 1 centimeter, depth to 0.2 and the height to 3, and I click on build select. So you can see that our block is ready. This is the X direction, this is the Z, and this is the Y direction. I want to make another block like this and rotate it by 90 degrees, so make an L shape. For this you can just right click on this and set a duplicate. Now we have two blocks over each other. Then you can come here and under the transforms find the option rotate. When you want to rotate an object, first you have to select that object. I select this. The next step would be to select the axis of rotation. Because I want to rotate it in this direction, the x-axis would be our rotation axis. Therefore, I set this to x-axis, and because I want to rotate it in the reverse direction of the angular coordinate, I set it to -90 and set build selected. You can see that one of the blocks are rotated by 90 degrees. Okay, very well. Now I want to copy this block and move it upward so these two bus bars have electrical contacts with each other. To make it better, I go to the ZY view. Here, if you click on YZ, you can see the YZ view. Okay, I want to copy this one upward. For this, I go to the transforms again, and here we have a copy. First, you should select what part you want to copy. Okay, come here and click. I want to this block be copied, and here you should define the displacement vector. I want this block to go, for example, 2 units upward and 0.2, for example, in the direction of Y or -0.2. I don't want to change anything in the X direction, so let it to be 0. In the Y direction, I set -0.2 centimeter, and in the Z direction, I set it to 2. If I build selected, okay, you can see that there's another block here, which is the rest of our bus bar, and they have electrical contact with each other in this point. Now I want to unite this block with this block to be one part. For this, I go here to booleans and partitions. This lets you to, for example, union two objects with each other, keep the intersection of those objects, or differentiate those objects and many other options. I select union, and here I select by clicking these two blocks and set build selected. Now if you go and stay on the object, you can see that both ones are selected with each other, which shows that you have one object. Notice that there are still two domains. If you want to select a domain, you should come here. Here you can select different options. If you want to select an object, you should choose this option. If you want to select domains, you should come here. Okay, you have two domains in this object. If you want, for example, select the boundaries, you can come here, and there you can select the boundaries and so on. And I want to make a little curvature in this side, so I go on the editing option, and here we have a fillet option. It transforms a pointy corner to a curvature, to a rounded corner. Okay, I select this one. It says me to select an edge. I select this edge. Okay, and this is the radius of the fillet. I set it to 0. For example 15 and build selected. You can see that this part has a curvature. Okay, now we are good to go. I want to, for example, ground one side, for example this side, and insert a voltage difference between this part and this part, and see how much current goes through this bus bar, and therefore calculate the resistance of this structure. At the final point, you should select form union or build all. Okay, our geometry is ready. Let's go to set the materials. Under the material, we need to define the electric permittivity and also the electric conductivity. I right click and select add materials from library. Under the library in the AC/DC, there is a material called copper. I double click on it, and the copper is set as default to our three domains, domain 1, domain 2, and domain 3. If you come here, you can see that many properties have been defined here, but only two of them have check mark: electrical conductivity and relative permittivity, the two things that the software needs to solve the electric current. Okay, our job in the material section is done. Now we go to define the physics options. The main equations that should be solved in all domains is called current conservation. If you come here to the equation, you can see that the software solves these three equations simultaneously in these three domains. This is the same equation that is solved in the electrostatic module, but these two are new. This is the current conservation formulas, and J equals sigma E. It is the main equation that is needed to solve in a conductive material. I let this to be. However, I should say our material type to solid type, because our materials are solid, they are copper, and the rest of options do not need any change. Please notice that you need the electric conductivity and also the relative permittivity. Now they are set to from material, but you can select here user defined. You can define the conductivity here as Siemens per meter, but if you select from material, it goes and select the one that is defined here. Let's come back to the physics. The default boundary conditions for all boundaries is the electrical insulation. If you see the equation, it is n.j equals 0. This means that each boundary that has this option, the current cannot go through this boundary, cannot go to this boundary or comes from this boundary. This means the electrical insulation. Okay, all the boundaries can have this option, but this side and this side should change. I right click on electric currents, and here you can see the ground boundary condition. I set this part to the ground. Okay, and if you see, because it was predefined in the electrical insulation, you can see a very small red rectangular here. It says that the boundaries that are under the ground also defined under the electrical insulation, but because the ground is at the bottom of electrical insulation, it overrides this condition. If I come here and go to 17, you can see that it is set overridden. But what? By ground. You can see here the red rectangle. Okay, also need the terminal boundary condition. I set this one to terminal and I feed 1 ampere current through this terminal. If you set the terminal type to current, the software automatically calculates the resistance, and if you set it to voltage, the software calculates electrical conductance of the structure. So I set it to current and set it to 1 ampere. The only thing that is remained is the contact point of these two bus bars. For that, I right click on electric currents. There is another boundary condition that is called electrical contact. If you set it, you should select a boundary that is between two domains. If you move your mouse here, you can see that nothing is selected except for this one and this one. If you click here on the transparency, you can better see the boundary between these two domains. Here there's one, and here there is another. If you don't set this one to electrical contacts, this is assumed to be one body. No resistance is set for this boundary, but I want to set a resistance for this point. If you select this, you can come here. I set it again to solid. There are different type of electrical contact resistance calculation. You can see the details in the help, but here you should set the surface roughness of the contact point, the average slope of the roughness, and also the average height, and also define the contact pressure, which means how much these two bus bars are pressured to each other, which is normally set in practice by screws. Now all the physics conditions are set. I go to the mesh and I set the mesh to extra fine, set build all, and now we are ready to compute our model. Okay, now we have the results. As you can see, the electric potential is shown in this 3D domain. If you click on this, you get back on the default viewpoint. As you can see, here is the 0 volt because it is grounded, and here is the maximum voltage which has been formed due to feeding 1 ampere through this structure, which is approximately 70 microvolt. If you want to get the resistance straightforward, you go here under the derived values, the global evaluation, and here select the replace expression. Under the electrical currents, under the terminals, you can find here the resistance. I double click on it and set evaluate, and you can here find the resistance mount. If I click here and add a U, this is set to micro, and you can see that the overall electrical resistance from here to here is about 70 micro ohms. If I come here and in the electrical contact increase the pressure between these two bus bars, I expect the resistance to become less. I set it to, for example, 200, set enter, and come here and compute again. Then I come here under the global evaluation and evaluate again, and you can see that the amount of resistance has been decreased a little bit. Okay, now I want to set a cut plane, for example here, and see the distribution of the current density over that surface. For this, I come to dataset, right click on it, and set the cut plane. This plane should be in the XY surface because I want to cut the bus bar in this surface, therefore I set it to XY. And Z coordinate, here is 2, for example, here is not bad, I set it to 4 centimeter and plot it. Okay, you can see the surface here. Now I click on results, add a 2D plot group. By default, it is tuned to cut plane 1. I'll right click on it and add surface type of plot. I click on replace expression under electrical currents. Here you can find the currents and charge, and this is the current density norm. It is the magnitude of the current density. I click on it and set plot, and you can see that the amount of current density is equal over the surface. This is the same thing that was explained on the physics description. Viscon effect or the proximity effect is ignored in this physics. Therefore, nothing will change the current density over the surface. The current goes through all the surface without any difference between different areas, and therefore this physics is only for calculating the simple resistance. If you increase the frequency, you don't notice a change in the resistance. I want to ask you to explore the other options in the 3D results view. For example, if you come here, you can see that different perpendicular surfaces are defined in the 3D body and electric field norm are shown here. And if you come here, you can see that here the electric field is quite constant, but at a contact point there is a change because the current goes from this side to this side. And if I click on this, on the multi slice, and I change it with the here current density norm and click on plot, you can see that I set it to YZ plane. You can see here that the current density is higher here, the current density is less here because higher cross section is available for the current to go through this, and in the rest of the bus bar the current remains the same. There are also an interesting point here. Here we have a bend in our bus bar, and you can see here that on the bend area the outer area has less current density compared to the inner area. This is an interesting point which should be considered in designing the bus bar. Okay, enough for this video. In my next video, I want to calculate the grounding resistance of an earth electrode. Enjoying this tutorial, please support our video by liking it and also subscribe to the channel for more in-depth COMSOL guides. Also, click on the notification bell so you don't miss out on our future videos. Take care and see you in my next video.